brace yourself. Things are about to get real. And what I mean by that, of course, is that we're going to change from thinking about vector spaces over GF2 to thinking about vector spaces over the real numbers. That's what you thought I meant, right? Probably not, but let's do it. So today's topic, as promised at the end of the last video, is we're going to talk about matrices that come from graphs. So we've looked at vector spaces that came from graphs. We saw at least one linear transformation between vector spaces that came from graphs. That was this kind of incidence matrix. And now we're going to look at the same incidence matrix. We're going to lift it up to think about it over the real numbers. And we're going to discover, in some sense, we're going to construct from scratch some other really important, interesting matrices that come from graphs. So we had the graph. We had this matrix, which was the incidence matrix. Now we're going to call it the boundary matrix, and it's going to have a new name because we changed it a little bit. You may notice there's some minus signs in here, and we didn't have minus signs when we were working over GF2. They're going to be tremendously useful, really essential for us when working over the reals. And from this boundary matrix, we're going to get the most important matrix that you can associate to a graph, which is the Laplacian. And that Laplacian will turn out to just be related to the degrees of the graph. You can see that this is degree 1, degree 3, degree 1, degree 1. And the adjacency matrix, which has, it's just a 1, 0 matrix, which has 1 if vertex I and vertex j are connected, and that is element ij is 1 if they're connected, and 0 otherwise. All right, so these are going to be 1, 2, 3, 4 different important matrices associated with a graph that we're going to cover right now. So, all right, here we go. So I said we're going to go from working over GF2 to working over R. How do we make this change? So previously, we saw this incidence matrix. Remember that it had a row for every vertex. So I had vertices 0, 1, 2, and 3, and a column for every edge. Here was edge 0, edge 1, and edge 2. And in each column, for each edge, it has the ones at the two endpoints of that edge. So edge 0 has, it goes 0 and 1, right? Edge 1 is between 0 and 2. Edge 2 is 0 and 3. That was fine and all. And one of the things we did with this was we added, if you added two edges, we could look at the result after applying B. And what would happen is that if they had a common endpoint, the common endpoint would cancel out. We would like to have this kind of canceling. In order to do it, actually, that's why we're going to instead make these edges 1 and then minus 1. All right, and this will now have a new symbol. This is our boundary matrix. Okay, it serves the same purpose. In some sense, over GF2, it's the same matrix. But I give it a different name just so we can be clear that we're talking about the matrix now over the reals. And this symbol here, this curly D, which you may have seen from calculus, is what you hope it is. It actually is a discrete kind of, well, let's say a discrete version of that operator that you see in calculus. All right, so what does this new boundary matrix do? In particular, we know that it was supposed to be a linear transformation from the vertex space to the edge space. And so I'm going to use these same symbols for our vertex space and the edge space over the reals, but now you should think of now the vertex space is now like Rn instead of just 0, 1 to the n. That is, when I look at a vector in the vertex space, I'm really assigning a real number to every vertex, where previously I was just assigning 1 or 0 as a way of indicating whether it was in a set or not. And similarly, the edge space is going to be, it's going to be Rm, right? So I'm assigning a real number to every edge. So one way to think about this is that a vector in VG is like having data on the vertices. I've assigned a real number to every vertex. And a vector y in the edge space is like having data on the edges, right? This y has a real number for every edge. Similarly, we can define the cycle space of G still to be the kernel of the boundary and cut space of G to be the image. So this is just the cycle space and the cut space over the reals and not over GF2. So we can look a little closer then at also at what is this linear transformation doing. So over the reals, as I said, we're going to think about vectors in the vertex space as assignments of a real number to every vertex. So here's vector x, and again, you should think of this x as being in VG, but like I said, this is also R4 because there are 4 vertices. So that means I put a 15 here, a -1 here, a 13 here, and a 2 here. Now, one thing I didn't mention is that when I defined this boundary matrix, I had to decide which vertex gets to be +1 and which one gets to be -1 for every edge. In a way, that's like picking a direction for every edge. It's going to turn out for that every time we use this, that direction is not going to matter so much. But for these examples, let's just say we arbitrarily pick a direction of these edges. So think about these edges. I think in this case, I picked them so they go from the higher number to the lower number. Okay, so I put a little arrow on every one of these edges to indicate it's often called the orientation of the graph. The graph is not a directed graph, it's still just a simple undirected graph, but we kind of give it an orientation so that we can define this boundary matrix. So if we were to just apply it directly, that is, I try to just take boundary transpose times x, what I'll get is for every edge in the graph, I should get a number, right? I should get something that gives me a real number for every edge in the graph. So this is going to be a vector in R5 because there are 5 edges. And for the first coordinate, it's going to be 15 minus -1. Okay, because one end, again, this is like having the 1 and then the -1 times this. The next one will be 15 minus 13. The next one will be -1 minus 13. Edge 3 will be -1 minus 2. And edge 4 will be 13 minus 2. And so if I write these all out, or if I do the arithmetic, I should say I get what? 16, 2, minus 14, minus 3, and 11. All right, stick with me for a second. So what did we just do? For each edge here, if you look at the direction it's going, this number, 16, is the amount that the function value changed as we traveled across that edge. So to go from, say, this vertex with value 13 to the one with value 15, we changed by 2, which is good because that's what we had here, 2. And similarly here, 13 to -1 is a -14. 2 to 13 is +11. And 2 to -1 is a -3. And so what happened is this multiplication by the transpose of the boundary matrix is like taking a derivative. It's telling us the difference, how the function value changed over a single step. And that intuition is not even really a stretch. It really is this kind of discrete derivative in the, and I'm going to put this in parentheses here, the oriented graph. And if you change the orientation, you would change the signs of the derivative. So you would get different values here, but only up to the sign. Let's do the other one, right? So if we just took the boundary matrix itself directly, that should give us a linear transformation between the edge space and the vertex space. So that is, I've got some data on the edges. I've got some numbers. And here I actually took the same numbers that we just computed for the same graph last time. And the result is, again, if I wrote out the whole boundary matrix here so that you can remember what it looks like. And if I do this whole multiplication, what I get now is 18 minus 28, 9, and minus 8. Hopefully my arithmetic is right. Done with that. Let's try this again. Here we go. So 16 plus 2 is 18. Minus 16 minus 14 is minus 30, minus 3 more is minus 33. Minus 2 plus 14 is 12, plus 11 is 23. And let's see, right to the end, 3 minus 11 is minus 8. Okay, if we check here, 18 is exactly the sum of all the values on the edges coming out of this vertex. And they're counted up by their orientation. So you can think about this as a flow, and this is the net amount of flow coming out of this vertex. Similarly, if I go to 1 here, this is minus 33. That is, there was 16 coming in. This minus 14 coming out is like 14 more coming in. So there's 16 coming in, 14 coming in, 3 more coming in. That gets us 33. And let's do the other ones real quick here. So this was 23, 11 coming out, 14 coming out, 2 coming in, sums up to 23. And here, the last one, minus 8, because I've got 11 coming in. It's like 11, it's like minus 11 plus 3. All right, so that's how we can think about this this boundary matrix. I almost said instance matrix. This boundary matrix as a linear transformation, taking us from data on the edges to data on the vertices. Now we can do something fantastic. We have 2 linear transformations. We have one from the vertex space to the edge space, and one from the edge space to the vertex space. And we could just compose them. And one of the wonderful things about matrix representations of linear transformations is that composition is just matrix multiplication. That's why matrix multiplication has this weird definition. It's just so that it, in a way, so that it corresponds to composition. Now, in this case, the composition in this order will give us a linear transformation from the vertex space to the vertex space. So that is like I take some function on the vertices, and I'll get a new function on the vertices. All right. At first, this just seems like an academic exercise, like why even do it? But let's just write down what this matrix is, and it'll turn out to be literally the most important matrix you can associate with a graph. All right. So if you want to work out what a matrix times another matrix is, you can often do it component-wise. So the ik entry in this matrix is going to be the sum of overall j in M of boundary ij, boundary transpose jk. And of course, this is just the boundary kj, if you like. If you want to get rid of the transpose, you just swap the two indices. Now, does this actually help us? Well, we can work out what the exact values are. One case that's interesting first is that if I and k are equal, that is on the diagonal of this matrix, we see that these two terms would be the same. So when is the boundary ij equal to something that's not 0? Well, only when vertex I is in edge j. So if I have a vertex I in an edge j, and then it'll be either a 1 or a -1, but in both cases I'll just get the square of that. So it'll count 1 for every edge that's incident to I. So this, if I just look at the case where I equals k, this sum is going to sum over all the edges, is going to get 1 for every edge that's incident to I. And well, we have a name for that. That's going to be the degree of the I, if I is equal to k. Now, if I is not equal to k, if it's some other pair of vertices, remember that the I and the k in this case are giving us indices of vertices. If there's no edge that connects I to k, then there was going to be no edge for which both of these terms are non-zero. Right? But if there is an edge ej that connects vertex I and vertex j, so in pictures that would look like vi, vk connected by ej. If there is such an edge, then one of these will be +1 and one of these will be -1. That's how we define the matrix. And in fact, there can only be one such edge. So of all this sum, only one of these terms could possibly be non-zero. And if it is non-zero, it's -1, and it's -1 in this case only if vi, vk is an edge in the graph. And now otherwise, for any other pair of vertices, if they're not connected by an edge, there will always be one of these two that will be 0 as you do the sum. So the whole thing will come out to be 0. All right, now this matrix, as I said in the beginning, is called the Laplacian. Now, this is not maybe the most common way to discover the Laplacian. Usually what happens is you just write down the definition and you say it's important and then kind of prove other facts about its relationship. But since we started with this incidence matrix as defining our cycle space and our cut space, and then when we look at it over the reals, we get this boundary matrix, I think this is maybe the way you might first encounter it in that direction. All right, so this matrix is a little funny, right? The diagonal is special, and then everything else just depends on whether there's an edge. And in fact, you can write this in the following form. If I look at the degrees of all the vertices, and I put those on the diagonal, and I look at the adjacency matrix, which again has a 1 in entry ij if the edge ij is in the graph, is in the graph. And so just to be clear here, AG, we're also thinking of this as an n by n matrix. This one as well is n by n. And the Laplacian, of course, is also n by n. But you can see from this that the Laplacian is just equal to this degree matrix minus the adjacency matrix. Okay, so you can think of, perhaps you've seen the adjacency matrix. As I said, it comes up in data structures classes or other places, but I think that the Laplacian is somehow more interesting. It contains the adjacency matrix, but also has this degree information. Now, we've seen that the degrees of a graph can be used to define an invariant of the graph. In fact, it's a pretty useful one for quickly trying to determine whether two graphs are isomorphic or not. But you may also recall that in order to use the degrees as an invariant, you had to sort them, that the ordering really mattered. And when we did all this, we kind of just picked an ordering on the vertices And if I picked a different ordering on the vertices, I would get a different matrix. So in the next video, we're going to look more at how to take these matrices and extract meaningful graph invariants from the matrices. We'll also see how some interesting computations happen with them. But before I do that, I'm going to answer a question. Now, usually, I guess, because these videos are recorded beforehand, it's pretty hard for these videos to be interactive. Like, it's hard for me to say, okay, do you have a question? And then answer the question. But this is one of the few times when I can do that. So what you can do is you could pause this right now, and you can think of a question that looks like the following. So something like, is this Laplacian matrix and this boundary operator like, and then fill in the blank. Is it like, something I saw in my electrical engineering class, or something I did in calculus, or something like that? So think of a question like, is this really just some version of some other theory that maybe I learned in another math class? Okay. Did you ask the question? Okay, so if you did, now I can answer it. So the answer is yes. Turns out this is exactly very closely related. It's actually a pretty interesting deep theory. And I can say that because no matter what you thought of, like, this is it, right? Like, the Laplacian comes up, it finds its way into almost everything. You could think of it as a discrete form of so many of the continuous things you may have studied. It gives you the foundations for things in, like studying electrical circuits, or random walks, or like heat flow, or anything in algebraic topology, and so many different topics. Like, the Laplacian is really the core, and so it's worth us studying. And it turns out that it also gives us a way to take problems which were purely combinatorial and start to really treat them as numerical problems. So when you think about solving systems of linear equations, that's like a numerical problem. It didn't seem so combinatorial. And so you can do this in both directions. You can take combinatorial problems on graphs, turn them into numerical problems on these matrices. But also another fun thing is that you can take purely numerical problems, like solving systems of linear equations, and go in reverse and try to turn them into graphs from matrices. So that's some fraction of that we'll get to see. We'll only get the littlest bit of the theory of graph Laplacians and what they're good for. But just know that these are really fundamental, important objects, and so I hope you like them.